walking on the darker side. He got to this position starting out at MIT, which is okay. He got bachelor's and PhD degrees there in experimental nuclear physics. What he did subsequently was to come to LBNL, and then he really went to the dark side, which is across the bay. Working as an assistant professor at Stanford. Thankfully, he realized that it was not the right place to be, and he moved to Lawrence Livermore.
They decided also I was not in the right place.
And actually made major contributions there, but then in 2009, he became the vice president and dean of research at the Naval Postgraduate School. And from there, that's when we were searching, and we were very lucky to bring him to the correct place after going to those two other universities. And we finally got him here to Berkeley, where he's been chair of our department. And at this point, I'll turn things over. Let's thank him.
Thanks, Darren. Okay. Thanks for reminding me of that pair, because, in fact, I think most people would agree that their lives, when you look retrospectively, do form some kind of large arc. Although Ed is our longest serving faculty member here, I was actually, well, there may be some older people here. I was, in fact, of our current faculty, the person who taught here first. Because when I was up at LDL, I just got my chair warm, and the phone rang, and it was Stan Prusen. And he said, "We're in a fix. We just had an unexpected retirement. We're 4 weeks out from the fall semester. Could you teach the graduate nuclear physics for us?" And I said, "Sure." They're sort of a brash young fellow. And then I came down. Stan and I became lifelong friends. He took me under his wing. He showed me how 201 was taught. And we had a grand time. And then he would show up with the students having lunch at Livermore. We got to know one another for years and years and years. And and I always had such admiration for Stan. So then I was at Naval Postgraduate School. This very idyllic place. It's a sort of a garden of delights, if you like, sort of, very high technology, DoD weaponry and stuff like that. It's just a marvelous place. And I just thought I would bleach my bones there. And then one day the phone rang. This was 30 some odd years later. And it was Stan. And he said, "Send me your CV. You're being applied for a job." I did not know that was a transitive verb, but anyway. He said, we need somebody who can be chair right out of the box. And I said, "But Stan, I'm a physicist, not an engineer." He says, "I have no time to talk. So send me your CV." So I sent in my CV, and I thought this madness would pass. And then 6 months later, after I'd forgotten about it, Junhong called up, and he said, "You're interviewing tomorrow." And I said, "How about next week?" He said, "Okay." So there we have it. So it was, 35 years later. And I was hoping by the time I taught 201 again, Stan would be there to shepherd me through. But, because I actually was much less sure of myself the second time than the first time. But anyway, it worked out passably well with Lee's help. I think this is an example, and I think we've heard, I think on 2 or 3 occasions in the past several years, we've had wonderful colloquia from Rick talking about his exploits on very basic science experiments, and quarry and so forth. I think one of the things very interesting about our department is it actually just shows the synergy between basic science. I think compared to practically any other program in the US, this is a very sciencey type of department. As you know, when the students come through here, and in the NEAB, our advisory board comes in the spring, and they talk with the students. They always come back to us and say, "You know what your students most like about this department, what's special about it is it's a very sciencey type of place." And he said, fundamentals are really valued here, and spin-offs from sort of the core mission of the program. Anyway, those of you from my epic will get it. But then I'm fairly long in the tooth. But anyway, that was Pink Floyd. I'm going to talk a little bit about the dark matter and the Axion, because I think this whole thing kind of begs the question You know, what's this activity have anything to do with kind of a mission-oriented type of department, or when this got started at Livermore, very similarly as well. I'll talk about the microwave cavity search for axionic dark matter, the prehistory, where we are today, and one final provocative thought. Oh, I was also reminded of, a few years ago, I actually was asked to be a graduation speaker for a small college, and just before I had to go out and give my talk, I was in the washroom there, and there were these couple of guys at the sinks there, and one guy turns to another and says, "Who's our graduation speaker today?" And the other guy says, "Oh, it's old Van Bibber." And the first guy says, "I wonder who canceled." I don't know who did cancel, but
Just wanted to take over.
all right. Back at Livermore, my boss, Dave Fortner, used to describe the laboratory. He said, why places like Livermore are so special. He called this the Eyeglasses diagram. And he said, whenever you have a place like Livermore, which is a mission-driven place, and I think nuclear engineering departments, in fact, have that same flavor in academia. He said you have this rather beautiful phenomenon that, you know, the country pays in to do really important missions. And you build up an infrastructure, computational, experimental infrastructure, to do things that a lot of other people don't do. And your best, many of your best folks are also going to have scientific pursuits at a national lab, and they will go out and go to conferences and work with people doing X-ray astronomy or quantum computing or whatnot. In the basic science world, they'll meet a whole new cadre of people. They will shine. The infrastructure that you build up in the national labs will allow you to compete and to win and to be a valued partner in basic science. Those things that you learn in the basic science world and new people that will spin back into the mission and make your ability to do the mission better. And so you have this virtuous cycle going back and forth between mission and basic science. And I think this is true of nuclear engineering departments as well. So let me tell you, first of all, a little bit about axions and dark matter. You probably know a little bit about dark matter. I think probably you know a lot about dark matter. You've heard a lot about the WIMP. I think for 30 years there's been very large investments. I think that the sort of the pioneers in this was an experiment that started, well, both here and at Berkeley, called CDMS, Bernard Sadolet and Blas Cabrera. And now you have these very, very large multi-ton liquid xenon detectors deep underground. Axions were always just as credible a dark matter candidate. It solved also its own set of problems in the standard model as well, but took time to get traction. And even now, I think we're still like the old, if you go back 30 years, drive down the highway, you would see signs like this, you know, we're number 2, but we try harder. We always consider ourselves as the kind of the Avis of dark matter particles. I want to come back to this later, but we now, in the past literally 20 years, everything we know and cherish and love, which is the galaxies, nebulae, stars, and so forth, life as it's evolved on planets and so forth, made of baryonic matter, atoms and so forth, has undergone a rude demotion. We now know that that stuff is less than 5%, probably 4% of the total energy density of the universe. The rest of it is in some form that we now are reasonably confident in some exotic, non-baryonic form. And even worse, this interloper, Saul Perlmutter, and his counterparts at Harvard, his team, and the counterpart team at Harvard have demonstrated now that in fact 2/3 of the energy density of the universe is not even matter at all, i.e. things with non-zero rest mass, but is in some mysterious form that might be Einstein's cosmological constant or some other dynamic field that we call the dark energy. And so we've undergone this rather rude demotion to being a very small fraction of the overall energy density of the universe. Now, we'll talk a little bit about evidence for dark matter right now, but when you talk with people, I think, obviously very, intelligent, literate people have heard something about this. They'll always point out, they say, you talk about evidence for dark matter, you talk about seeing dark matter, but by definition is something you can't see. What do you mean by that? How can you see something that you don't see? And one of my greatest, I think, demonstrations of this, this is Reinhard Genzel, who's an astronomer that splits his time between Berkeley and Germany. And he has made a career in recent years, many years, from the assets of the European Southern Observatory, peering into the galactic center in the near infrared. Now, the disk of the Milky Way is very dusty, and you can't see right into the center of the galaxy in the optical, but you can in the infrared, where you get less scattering. So what he has done, this is not a simulation, this is a real movie I'm going to show you, is that he's taken a picture every few weeks for more than 10 years and stitched the pictures together into a video, and you actually see motion. Now, I want you to look at a couple of things. We're going to look at this thing, then we're going to zoom in and continue looking. Keep your eyes on a couple of things. This is a clock that's going to move very rapidly. It's going to move about 10 years in about 10 seconds. And then look at this little bar. That's a very tiny distance, 10 light days. It's really, really, really close into the galactic center. And give your impressions on what you see. Now we're going to zoom in. Odd. What's odd?
Well, it's orbiting.
What?
It's orbiting.
Yes. Even, I remember showing this to my sister, who had no particular training in physical science. She's a glass artist, and she said, there's something there. In fact, right there, it's the foci of that. In fact, if you do a simple calculation, non-relativistic calculation, you take that as a scale bar, and this period being about 10 years, you can make a very rough estimate that this thing here, in fact, this is the central black hole of our galaxy of several million solar masses, 3 or 4 million solar masses. Now, black holes are not a significant part of the dark matter story. There may be 1 part in 10 to the 4, but it's just a nice example of how you, quote unquote, see something that you can't see. So how did this begin? Exhibit A, Fritz Zwicky, Bulgarian-born Swiss astronomer, spent most of his career at Caltech, and he takes a leaf out of the book of Festus Slipher and Edwin Hubble. This is the early 30s. This is now becoming an industry of using spectroscopy on distant objects to look at the precession velocity by the Doppler shift. Now, actually, the thing you should observe right away, this is sort of like a Rorschach test. Just take a quick look at him and let your mind form a mental picture. You're right. This guy was an absolute character. He was a string tie and all. He was sort of a kind of a irascible but lovable, absolutely brilliant astronomer, one of the best of his generation, one of the best astronomers of the 20th century. But he was an absolute character. And so many photographs of him, when he was sort of candid photographs, he's kind of going like that. Now, when you and I go like that, it means perfect, great. When he's going like this, he's saying, that guy is a spherical bastard. He says, Fritz, what do you mean? He says, he's a 4-pi bastard. He's a bastard no matter how you look at him. So that was his impression of almost everybody. Anyway, so what he does for the first time is that he takes the Coma cluster, about 1,000 galaxies here, and he uses the Doppler shift technique to look at the radial component of the velocity, and immediately it comes to him, this picture does not square. He's looking at velocities 500, 600, 700, 800 kilometers a second. If you say, well, these galaxies, rather garden variety of galaxies, not terribly different from our Milky Way, maybe 100 billion stars. We know what galaxies weigh. There is not enough gravitating mass associated with those galaxies to explain why the cluster is gravitationally bound. And you see this all the time. You see, it's not simply like an accidental confluence of images or smudges on your photographic plate. These things are really gravitationally bound, but they could not be bound with that variable velocity there unless there was a great deal more mass than you were looking at. And the discrepancy was close to an order of magnitude, about a factor of 7. And we see this again and again and again. Okay, now, he was much too good an astronomer to be lightly dismissed, but people could say, yeah, I mean, galactic clusters are a bit like a swarm of gnats or mosquitoes you see on a summer day. You're walking down the sidewalk and you see this kind of sphere moving at you. It's sort of disorganized motion, but people say, well, it's complicated. You know, maybe there's something going on we don't understand. We're not going to gainsay Professor Zwicky, but we're not quite sold yet. 30 years later, the picture becomes much more crisp. This was our colleague Vera Rubin, just died about Christmas or so. So very, very distinguished astronomer. I think in many people's opinion, and certainly mine, I think should have been very deserving of the Nobel Prize for her work. Of many other accolades she received, the one she didn't receive. She and Kent Ford, her collaborator, then looked at the population of what is now about 1,000 galaxies, spiral galaxies, which are close enough that you could actually resolve their angular distance. They're not just a point of light or a smudge. They're large enough that you can now take the focal plane of your telescope and now kind of do lineouts and look when these things are relatively edge on and use the Doppler shift method to measure what's called the rotation curve. Now, as a preamble, if I do a freshman physics problem and say, okay, plot the velocity and the distance of the 9 or 8 or 9 planets there, and calculate the Keplerian motion you would expect for them. The sun has, is the only gravitating object there. The others are just small potatoes and can be safely ignored. You get this 1 over root of r fall off. And that's exactly the line. That's not a fit. That's not a fudge or anything. The curve really does go through all those points, even though some of these things are a little bit elliptical. Absolutely perfect, right on. Pluto, for example, has a year which is about 250 times longer than the Earth year. It's 40 times further out, and it's traveling square root of 40 slower. So 6 times 40, a much, much longer year. What they see in every case, you would expect that if I got far enough out, looking at the optical or the hydrogen 21 centimeter line when there's no longer any optical to look at some point this curve has to turn down like that. And the fact is it never does. In the 1,000 or so cases we've measured, the rotation curves are flat or even increasing very mildly like that. Again, this is kind of a WYSIWYG system. Here, what you see is much less than what you got. The discrepancy is about a factor of 10, a little bit less than 10, maybe a factor of 7. And to crown it all, here's Tony Tyson, kind of began his work at Bell Labs many years ago with the Hubble Space Telescope. He's been at UC Davis since, I think, about 15 years, and as sort of the chief scientist for the Large Synoptic Survey Telescope, which is this humongous light funnel. It's going to be, it's under construction in Chile. In terms of what's called the entendu, the product of solid angle and aperture, it's enormous. It will look at stars over 10 years all the way down to the 28th magnitude, measure them night after night for most of the visible sky. It's a phenomenal instrument. What he has done here with the HSST is he's actually able to see these little arcing of back layers, these little blue galaxies here, which are multiply imaged. These are called Einstein rings. And by seeing how many and the degree to which these little background galaxies are imaged and stretched and where they are, you throw this into a computer and you calculate for 40 days and 40 nights, and out of the back end comes a mass distribution where you see not only the additional mass ascribed to the halos of the individual galaxies, but you see a distributed mass not attributable to any particular halo, but associated with the whole galactic cluster. Once again, you come up with some number about a factor of 7 more mass than is associated with the visible mass. About 20 years after, 15 years or so after Zwicky, we have a gang here at General Electric. There's Robert Alpher, Hans Bethe, George Gamow, and Robert Herman, student of Alpher's here. And they, for the first time, say, well, if we take this thing of the Big Bang seriously, let's calculate the networks of light nuclear reactions. This is sort of like 101, and then NE 101. And then you evolve this thing as the universe is cooling and expanding, and you end up in the back end with a series of isotopes, hydrogen to helium to deuterium, helium-3, and so forth, lithium-7. And everything fits very well with the primordial populations one could observe right now in top 2 stars, with the proviso that you're in a baryon-poor universe as a starting condition. So it only works if, in case that what's called the entropy to baryon ratio, or the baryon to entropy ratio, indicates an initially baryon-poor universe. Again, this factor of about 7. Okay, so that's where we get this. The thing is, we don't know what it is. It might be these things called WIMPs that have been handsomely supported. Many teams around the world, many large experiments, or this poor band, ragtag band of those of us who have been looking for axions, but are now beginning to get some traction as the bloom seems to be going off the rows of the WIMP. Supersymmetric particles have not yet been seen at the Large Hadron Collider. Larger and larger and larger detectors underground are not seeing any evidence for these WIMPs. It's still a worthy enterprise to continue looking for them, but the funding agencies are now saying we need to do a better job balancing our portfolio, and we're now seeing a little bit greater funding than we were some years ago. Okay, so let's talk a bit about the Axion. This will be the only kind of technical part here. The Axion is not an easily understood particle. It sort of defies sort of traditional interpretation of particles that were created thermally at the time of the Big Bang, like the WIMP. But our colleague Pierre Sakivi, a very famous theorist, Belgian theorist at the University of Florida, wrote a popular piece in Physics Today about 20 years ago. And it's a delightful kind of sort of parable or fable or kind of metaphor for how to understand how the axion comes to be in the early universe, what are its mass and couplings, and what is our strategy for looking for it. And this all comes out of this very simple article that he's done called The Pool Table Analogy to Axion Physics. And so the story begins with these graduate students who in their free time, their recreation, play billiards. Now, the thing to keep in mind is these are not graduate students on planet Earth. These are graduate students on Mars, on the surface of Mars. And they have ordered a pool table, a catalog off-the-shelf pool table that's flown over on a rocket ship, lands on the surface of Mars, and that it's plunked down in some arbitrary place, and they play pool. And most of the graduate students play pool happily without any concern for a very fundamental and very strange fact that only one graduate student seems to be cognizant of. And this graduate student, called TSP, the Thinking Snookers player, says, why is it that I take an off-the-shelf, standard, one-size-fits-all pool table, place it down on the Martian surface, and the pool table is flat to 1 part in 10 to the 11th. Now, there's a heavy black cloth sort of concealing the underside of the table, so you can't see what's going on. But Mars, like the Earth, is, if you've seen pictures from Mars rover, is mountainous, it's got valleys, hills, and so forth. You have 2 vectors at play. You have the local normal vector, and then you have the local gravitational vector. There's an angle between them. There's no reason why that angle should be 0. So TSP comes up with a hypothesis, and he said, if I had a company to build a pool table that could be placed in an arbitrary location and be flat to 1 part 10 to the 11th, what would I do? He said, trivial. I would simply put a heavy weight on a large pendulum here. One would not need to particularly care how long the pendulum is, but sufficiently long pendulum and a weight here, and this thing will enforce the table to be absolutely flat. So then TSP says, okay, my hypothesis, this is my hypothesis, I'm going to test it by smacking the ball into the bumper. If my hypothesis is correct, I will be able to induce an oscillation in the table, and the presence of these oscillations will indicate that my hypothesis is correct. Turns out he fails. But TSP is smart enough to say, okay, that doesn't invalidate the hypothesis. It could be that the length of this lever arm here is sufficiently long that I could not cope with my puny impulse to excite an oscillation that would be visible. Then he has the critical insight. And the critical insight is, okay, this thing is coming over on a rocket ship. One could even imagine making good use of time and assembling the thing from a kit in flight. While the thing is most of its journey of 20 months or whatever coming over, it's in a weightless environment internal to the rocket. You have the axis of the pool table and the axis of the rocket, and they need not be co-aligned. And you have an angle in the problem, but that angle has no physical significance. But when the time comes that this thing lands on the Martian surface, this thing fires its thrusters, and an astronaut in the rocket ship will then notice that the effective local Martian gravity will go from 0 adiabatically up to its asymptotic limit, like so. As you fire the thrusters, things slows down and finally comes to rest on the Martian surface. Now, those of us of a certain age always found this a bit quaint, because when we were kids in the 1950s, Flash Gordon and people like that had rockets which landed butt end like this, and of course all sensible space programs like the Russians and the US always deorbited things and they landed in a snowfield or landed in an ocean. Interestingly, Per's favorite company, SpaceX, Elon Musk is now landing his rockets butt end down to be reusable. So in fact, this thing's all come around full circle. Interestingly, here's the thing. Now when I turn on the effects of gravity, any misalignment angle between the orientation of the pool table and the orientation of the body axis of the rocket is very significant. And as you turn on gravity, you end up with basically a damp-driven oscillator like that. So ultimately, the pendulum oscillates around this special angle here at the aligning the thing with the gravity, but there is some remnant oscillation in the pool table. And so his experiment is, if my hypothesis is correct, no matter how tiny those oscillations are, I'm going to mount up a high Q oscillator. It could be a spring in the mass, and I'm going to change in very small steps either the mass or change the spring constant, however you want to do it. And if my hypothesis is correct, at this special frequency here, unknown, I will see a resonant translation of energy, a resonant transfer of energy from these very minuscule oscillations in the pool table into the high Q oscillator. This is a major paradigm for experimental physics. I think some of you, Rick made me remember a famous book by Grudinsky in the 60s called The Role of High-Q Oscillators in Experimental Physics. It's a paradigm that's used again and again and again. And I remember Bill Fairbank at Stanford many years ago. He had at that time, the world's largest gravity wave bars, cooled down to like 10 millikelvin. And you're looking for an oscillation of this thing at the level of 10 to the minus 18 centimeters or so. And he was reading it out by a little drumhead, sort of a very thin shim of metal, about this big, with a squid next to it, with the idea being that you can calculate that this very tiny oscillation, sort of a couple oscillator thing, would build up a physically measurable oscillation in this high-Q little drumhead like that. Of course, they didn't see anything at the time. Okay, nuclear physics, just one technical slide, and we'll get on and look at the experiment here. Here's the issue. In the theory of the strong interaction, this is QCD here, there is an awkward term called the theta term. Theta plays the role of a phase that goes between 0 and 2 pi, which violates CP symmetry, the product symmetry of charge and parity. So in fact, you can see that this is a real issue. It's a real issue in the following way. In the case of, so this would be CP violating and therefore T violating as well. If, in fact, I have a neutron magnetic dipole, if I had a neutron electric dipole, i.e. a physical separation of the charge distribution in the neutron like so, that would, ready-made, give rise to a violation of charge parity conservation. Oddly, very oddly, beginning with experiments done by Ramsey starting around 1950 and done to this day, the charge dipole moment on the neutron is way, 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 way down. It's about now 11 orders of magnitude smaller than the estimate you'd get if you said you pick a random number out of a hat between 0 and 2 pi. That would be a number on order of unity. That would give rise to a neutron electric dipole moment of about 10 to the minus 15 e centimeters. Now you could say it's like the pool table. You could say, it's just double up. You know, you spun the roulette wheel. Theta turns out to be some value that's exactly some special value to 1 part in 10 to the 11th. Or you could say there's a dynamical reason why this is so. Two young theorists at SLAC in the 1970s, Roberto Bethe, later Vice Chancellor for Research at UCLA, and Helen Quinn at SLAC. She was APS president some years ago, members of the National Academy, came up with a very interesting and very appealing theory. And in schematic, basically they say, let's allow theta to be a dynamical variable. It's not just a parameter. At some high temperature scale, very high temperatures here, you have a spontaneous symmetry breaking. Every point in space picks out a value of theta, subject to the condition to be sort of continuously connected. But at these high temperatures of the theory, in fact, this is just like the rocket ship in a gravity-free environment. It's an angle that has no particular physical significance. But 100 nanoseconds after the Big Bang, the universe cools. You end up down at QCD time, temperatures below a GeV, you get this very special and very strange feature of QCD. You get this infinite washboard potential, what are called instantons, that give rise to a periodic potential like this. Now theta says, I'm out of place. Theta rolls down, and around the CP conserving minimum, and the remnant oscillations, as realized by Weinberg and Wilczek, in fact give rise to the Axion, or the Axion. So just to complete the analogy here, the Axion is like a neutral, it's sort of a light cousin of the pi zero, but instead of being 135 MeV, it might be a micro eV, 10 micro eV, milli eV, or so. You have couplings are proportional to mass. They're both proportional to 1 over the symmetry breaking scale. In the same way that if I have a longer and longer pendulum, the intrinsic frequency of the table goes down, and all couplings to the table will go down. It becomes more and more difficult to excite a vibration of the table. So you have a linear relationship between the mass and the coupling constant from axions to photons. You have, in the same way with the pool table, a bound from overclosure. If the pendulum for a given offset angle is too long, or the longer the pendulum is, the more energy you have, potential energy stored up in the misalignment angle. Same thing here too, you have an early universe problem as well. If the symmetry breaking scale is too high and the mass is too low, then in fact you overclose the universe with axions. And of course we know that doesn't happen because omega total is unity. Omega matter is just even a third of that. We had a birthday, a 30th birthday a few days ago. Rick, when was it exactly? Supernova 1987.
Not exactly.
It was either late February or early March. It was when we saw the supernova 1987A. We saw this beautiful kind of rattling out of photons, 20 neutrinos in about 10 seconds at 2 large detectors, Kamiokande and IMB at Lake Erie. Perfect accord with the stellar cooling, protocore stellar cooling. Had axions been able to compete with the neutrinos, it would have quenched the pulse. And therefore, we are able to set a limit that the axion does not couple overly strong, and therefore has a mass that's probably less than something like 10 millieV or so. You also have conventional limits from stellar cooling. And so you end up with a nice situation. Well, I call it a good news, bad news situation. You actually have a bounded parameter space. You know what it takes to do the job. When you've done the job, you either find the axiom or you rule it out. Bad news, those are just really, really, really tiny couplings. Couplings so tiny that it's impossible to do experiments at accelerators with reactors. Now, most people say, well, gee, the pi zero decays into 2 back-to-back photons. Why don't you make life easy on yourself? Take a radio dish, stare out through the halo, or look at somebody else's halo. If the dark matter's there, eventually it will decay into back-to-back photons. And you will see a monoenergetic line at half the mass with a little bit of virial spreading, about 1 part in 10 to the 6th. And if it's not identified with any molecular line sort of from the intergalactic space or from your own atmosphere, then voila, that's probably the axion. Problematically, for such light particles, the free space lifetime is just abysmal, just hopelessly too long. And so here's where Pierre Sakivi writes this beautiful paper in 1983, which set off the whole field for how we look for the axion these days. He said, look at a magnet. You can, in quantum electrodynamics, you can model a magnet as a sea of virtual photons. And therefore, you can have a pseudoscalar, like a pi zero or an axion, roll from the photon state into the axion state and back and forth. An axion can convert into a photon, and a photon into an axion, but a single photon carrying the full energy. That changes everything. And the ability to, for an axion to roll from an axion state into the photon state or vice versa over a large extended magnetic field, and being a 2-body rather than a 3-body issue, dramatically increases the conversion probability. And so this is the experiment that Sakivi proposed in this very short paper, almost 35 years ago now. 3 elements. Very strong superconducting magnet, a high Q cavity, and then state-of-the-art microwave amplifier. And then it's just, as I like to describe it, it's basically your car radio on steroids. It's nothing more complicated than a heterodyne radio, but everything done to the nines, everything cooled down to absolute zero, and an amplifier which is operating at the limits of quantum mechanics. And in fact, there is in fact a limit for a standard linear amplifier on how quiet that the amplifier can be, just set by quantum mechanics. No. We're not doing that. Where's my... Right. So the signal you're looking for, it's a bit like being in the desert, very far from any cities, and tuning your radio, car radio, very slowly, and all you hear is noise. And you tune very slowly, and you hope to hear some excess power above the noise in a very narrow, but not perfectly narrow line. So it'd be narrow to about 1 part in 10 to the 6th, just due to the variable velocity of the dark matter in the halo. So you'd be looking within the bandpass of the cavity for a line that might be narrower by a factor of 10 than the conventional Q you would get from a copper cavity, even near absolute zero temperature. And then you would step tune this every several minutes. You simply bump the frequency like this, and you do this year in and year out. And then you measure power spectrum, do a fast Fourier transform, and look for the signal. Here's the bad news. The signal you're looking for might be like a billionth of a trillionth of a watt. It's a very tiny signal. Interestingly, that is tractable within the technology we have today. With the magnets we can do today, with the amplifiers, with the cavities, we can actually measure that. Now, the signal to noise is not simply an issue of the conversion power, which primarily depends on how big a magnet you can pay for. Obviously depends, like all such problems, on how low you can drive the system noise temperature down. And that's going to be both the black body contribution and then the amplifier contribution, limited by what's called the standard quantum limit of quantum mechanics. So let me tell you a little bit about the prehistory here, how I got involved. I'm actually doing a review. I'm leaving tomorrow to take part in a review of the nuclear engineering program at the University of Florida. I gave a talk there a number of months ago. Actually, just a stone's throw from the building is Williamson Hall, where I was collaborating with my friends many, many years ago, University of Florida. This is Chris Hodman, who's been a long-time employee at Livermore now. In one of the 2 first experiments in the world of this type, that's a magnet, a superconducting magnet you can pick up with one hand. It's about 40 pounds. And a copper, sort of a cavity that was kind of soldered together or brazed together about the size of a large thermos bottle. Amplifiers at the time were not very good. They had a noise temperature of between 5 and 20 Kelvin. They're called HEMPs, high electron mobility transistors. They're basically heterojunction transistors. All fit inside this can. But this and their competing team, this is now at Brookhaven. That's Adrian Melosinos, a real champion. He's still full of ideas, close to 90, professor at the University of Rochester. He built up a competing team, Rochester Brookhaven Fermi Lab, that in the old superconducting magnet building at Brookhaven. And these 2 teams were developing the strategy and the technologies, which are pretty much the way we do the experiment today. These were standing on the shoulders of giants here. So Adrian, I was not involved in this. Adrian in 1989 calls a workshop at Brookhaven. I got invited to it. I had some other nutty way of looking for axions. So I show up there, and he is a real kind of take charge guy. He's got this large table. He brought in magnet experts, amplifier experts, cavity experts. And the question was, in 2.5 days, where are we now? What does the theory say? And is the technology ripe enough that we could mount a next generation experiment that could actually reach down into the promised land, get down into the model band of the axion photon coupling that I showed you before. And it was a really interesting workshop. I hadn't really bought into this. But then he went around the table and he said, "Are you in or are you out?" And he said, "In or out, in or out, in or out." So he went around the table, and finally he pointed at me, and I said, "Oh, okay." So I'll try it out with this guy. And finally I realized, Adrian, you didn't declare your own intentions. He said, oh, no, this is too much like hard work. It's for you young kids. I just wanted to write a book about this. So anyway, he wrote a book. This is the proceedings. I still have it on my shelf. But here was the interesting thing. Then they turned to me and they said, well, Van Bibber, you own these big magnets at Livermore. I said, I do. And then Adrian trots out a view graph that you saw last week. The MFTFB. It's the size of a submarine. He said, yeah, they turned this thing on and they're decommissioning it. And he said, I want you to go back and talk to the bosses, and I want you to get us these two magnets. These are the Axion magnets. They're 25 tons each, about a meter and a quarter diameter, about a meter height, and I think about a 7 Tesla field. So I kind of went back, and in fact, I was sort of elected as the ringleader of this thing that I had no intention of working on, but that's how this whole thing got going. So I went back and set up a meeting with Keith Thomason, who was the fusion energy program leader at the time. And I was thinking, what am I doing here? Asking, so basically we were going to do an appendectomy on this huge tank and pull these magnets out. So I thought a little humor would go far. So I actually opened my presentation with a slide. It was a Gary Larson cartoon. And I said, because it actually did look exactly like this. I said, Keith, I need these magnets. And everyone in the room laughed. He said, yeah, we've got the same crew working on this as I've got working on my fusion machine. He said, if you can get the magnets out, they're yours. So anyway, so that's how the thing got going. Thus, we started burning up money. We had a bunch of technicians and engineers making a conceptual design for this thing. We had some crazy scheme for ganging together 10 to the 10th cavities and filling up the volume here. And we submitted a proposal to the Department of Energy. And the proposal was rightfully dropped on its head. And in retrospect, you think about it, the only thing I can say is, what were we thinking? 50 tons of magnets, a big cryo plant. Our collaborators from the Soviet Union were supposed to deliver all the cavities on time and on budget for us. A very large team of engineers and technicians at Livermore that can spend money faster than you can burn it. The whole thing being led by physicists with no discernible project management. We claimed it could all be done for $1 million. So anyway, the DOE kind of turned it down. But what came out of this was really quite good. Now, it was interesting, coded to this story. Who was the reviewer that dumped the proposal? Adrian Melosinos. So the same guy who kind of pushed us forward to write the proposal was the one who received it and finally declined the proposal. But anyway, that got the ball going, and now we have the experiments today. So we finally right-sized this experiment. Starting around 1992, we started building up a medium-sized experiment. We finally got buy-in from MIT, where Rosenberg was at the time. I was at Livermore, we were co-spokes. DOE bought into it. This thing ran very well for several years. Now uses much more modern amplifiers. It's a much larger experiment, about a 6-ton magnet. It's now been moved a few years ago to the University of Washington. It's a great tribute to Rosenberg and his team. It's one of the, I think, the great electronicers on the planet. If you look at the noise as a function of integration time, it falls exactly like Dicky's radiometer equation out to a month, like this. You could actually see a single additional RF photon per month, per minute above noise with this device. In fact, I talked with Larry Lasher, project manager for Pioneer 10, and who was still alive at least 10 years ago. When Pioneer 10 crossed beyond the orbit of Pluto, about 2001 or so, now it's even further away, the signal that was picked up from its last 4-watt onboard transmitter was about 10 to the minus 21 watts. And of course, you know the frequency was transmitting at. Our job is to look for a signal that might be 2 orders of magnitude smaller than that. and we don't know within 3 orders of magnitude what frequency. That's the job. John Clark here on campus learned how to turn a magnetometer into a gigahertz amplifier. They sort of gave new life to this experiment, at least in the gigahertz range. What was frustrating to me is that, however, after many years, we only got down, we got partway into the band, and by the way, we did not cover much mass range and frequency, much less 3 orders of magnitude. So at the Festria for Sakivi, I sort of led a community discussion and said, you know, guys, we need a special team to look higher up in mass. We got Steve Lamoureux for Yale involved. This is kind of like Skunkworks, it's sort of like a garage startup, no formal DOE project management, just a few friends doing physics. We went to Steve's blackboard in an afternoon, we kind of drew up what the experiment looked like, and that drawing remained there for about 6 months before he erased it. NSF funded it. It's a beautiful experiment from a cold start in 5 years. Berkeley led the team building the RF, building microwave cavities. Our little cavity shop is down in 1140. Conrad Lehnert, one of the world's wizards on quantum and subquantum limited amplifiers, built us the Justice and parametric amplifiers appropriate for the higher frequency range. And then Yale was the one ring that binds them all that actually assembled and integrated the experiment. We had one interesting lesson we learned. In May of last year, believe it or not, there was a freak snowstorm in the Northeast. The emergency power on campus went off. Within minutes, predictably, these things were with a cryomechanically cooled magnet. The magnet began to heat up, went above the transition point, and the magnet quenched. And the effect of the magnet quench is sort of like throwing a hand grenade into the cryostat. It wreaked havoc like you wouldn't believe. Interestingly, nothing valuable was destroyed. The amplifier survived, the cavities survived, and miracle of miracles, the dilution refrigerator, the very fine capillary wire tubes and so forth, survived. It was, anyway, we got the thing put back together. There's some data, and this year, we published our first data here at this next highest frequency range. We're beginning to scan up and down from there. Very near where we wanted to be with this very small experiment. It was picked up as an editor's suggestion and an APS highlight. It was just published about a month ago. And when I came here, actually, I wanted to make a clean break with my past and go back to the love of my youth neutrons. But it's like Michael Corleone in The Godfather says, just when I thought I was out, they pulled me back in. I discovered coming to Berkeley, I was in a privileged place to add value to this experiment. And I'll give you a couple of examples, and this is why, the interface of engineering and science. For years, I had said, the problem with this thing is we're operating the cavity in a very highly over-moded region, where as we tune the cavity, the mode of choice, the TM010 mode, we move it up and down, it's going through a complete forest of TE modes, and they're mixing, and you just have no clean space where the mode can be cleanly identified and not be hybridized with TE modes. And I said, I had heard about these photonic bandgap cavities, which are able to trap TM modes and radiate the TE modes away. And then I discovered my office is 50 yards away from the famous Elliot Gamow here, who's a very famous guy, just won the Newton Prize, who's the inventor of the photonic bandgap principle. And so this is a guy I revered, went over and talked with him, and I was shocked. He said, I've been reading your papers for years. You need me. So in fact, I actually got him, yes, we do, and we actually got him to give us some consultation advice. We designed, I recruited Sammy Lewis from MIT. She worked in Rick Temkin's group, where what they do is photonic bandgap resonators for accelerators and microwave tubes and gyrotrons. We actually now have a working prototype, and voila, that is a pure TM010, 011, 012. When you tune the cavity, all those things move in unison. There are no discernible TE modes. So this is the kind of thing when why you place like Berkeley is very special, you know, for applying really high engineering to science. Ditto, I all of a sudden realized I'm in the same department with a person I had worked with years ago when we were building the PEP2B factory at SLAC, Kaolung. He's the guy that performed the magic of coating the inside of 2.2 kilometers of beam pipe with titanium nitride, kind of a mass production but precision RF plasma deposition system, which saved this, you know, the project from, you know, from failure because of the intense synchrotron radiation would kick out so many electrons, you get this electron instability in the ring. He found a way of suppressing it. So I went to him and said, by the way, I've always wanted to put a thin film superconducting on the inside of a cavity. Can you do it? And then sure enough, we all of a sudden built up a system down there where we're able to build up very, very thin layers, monolayers of niobium titanium nitride, which will sustain a 10 Tesla field parallel to the surface like that. So we're actually working on making high Q cavities that way too. Another good reason why you can do high science at a wonderful school like Berkeley. Let me just show you one thing here, final provocative thought. I never forget, I remember the president giving a speech why he had he decided to launch the Super Collider project. He talked with his friend Kenny Stabler, former star quarterback for the Oakland Raiders in the 1970s. And he said, Kenny, the scientists want to build a super collider. Should we do it? And his answer is, throw deep, Mr. President. So anyway, some of us had a meeting, Sammy and Maria Simonovska and I had a meeting late last week with some of our colleagues at Stanford, Peter Graham, Kent Irwin, who are thinking very boldly on this problem. The calculation goes, imagine if you could continuously convert all the dark matter within the 1 de Broglie wavelength of your detector, each passage time as the Axion wind blows through your laboratory. The calculation is very interesting. That's a megawatt of power. The question is, could you do it? And they're not discounting the fact that you could actually do that. And we're actually looking at how that might happen. This would be the supreme infinite free lunch. You could just have a persistent current magnet here, no power in, out comes microwave power. That's the kind of thing nuclear engineering department should be working on. Anyway, thank you. By the way, if you want to read an interesting book by Richard Panik, The 4% Universe, he actually spends an entire chapter on our experiment when it was at Livermore called The Curse of the Bambino. If you're a baseball fan, I think you'll catch the illusion. He actually figured out that everybody on the ADMX team at the time was a Red Sox fan. He said, this is a particle only a Red Sox fan, good luck. Most of it is about Saul Perlmutter and Adam Rees and Brian Schmidt, this intense competition that happened between Berkeley and Harvard on the dark energy story. It's a kind of salacious read. It was a pretty brutal competition, but it's a good read if you like popular histories of science. And again, many thanks to our sponsors. All right.
Questions?
Perfectly clear. Perfectly clear.
So when do you discover? How long will it take to confirm or deny the existence of the problem?
It's like all things, the most probable time for the discovery is right now, actually, when you think about it. There's many things in statistics are like that. We're now getting the scan speed up to the point where we think we could do the job in the sweet spot of the mass range in 5 to 10 years. So I think that would be fine. Okay. If Steve Lamoureux ever gets tired of hosting the experiment at Yale, we would love to move down to 1140. So talk to the stakeholders group about that. Okay, I have to administer an exam. Okay.